So, what am I going to be talking about? Well, that's the title that I submitted. And the title has changed very, very slightly. I'll see if you can spot the difference. It's not quite as big a rickroll as John's switch from XML to dependent types, but it's a small but subtle change. And the reason it's changed is because basically when I put the talk together, I was following down one track of taking the TypeClass derivation stuff that existed in shapeless 2. I was trying to generalize that and make that more flexible, more general. And in the process of doing it, I actually realized that actually there was a set of primitives even more fundamental than the typeclass, which actually made everything super simple and super easy and super general. And it actually turns out now that what was once the typeclass in shapeless is now basically a more or less a kind of backwards compatibility layer on top of the new, more primitive API. So anyway, what am I going to be talking about? Well, I'm going to be talking about typeclass derivation for Scala ADTs, algebraic data types. So what exactly is that about? Okay, well, it's about algebraic data types, which are things of this form in Scala. So these correspond to sort of Haskell algebraic data types. The way that we represent them in Scala is by some variation on, but something very close to this, a sealed abstract trait, which maybe defines some protocol, maybe is completely bare, which is then extended by one or more case classes and case objects. And so we end up with a structure like this. This is very familiar to everybody. ADTs, as they are understood in shapeless, correspond more or less exactly to this. There are a couple of generalizations to this which arrived in shapeless 2.1, which don't really, well, I mean, there is a very, very deliberate restriction in shapeless 2 treating algebraic data types rather than all types in general. The generalization was just enough to allow for non-case classes but with lazy members. Case classes aren't allowed to have lazy members, and it means that there's a whole bunch of things that you might like to be able to represent via an ADT using, say, for example, trying to construct cyclic data structures, graphs and things like that, which you absolutely have to have lazy members to be able to do, and which can't be represented by traditional case classes. But I needed to be able to expand the range of types that was amenable to this kind of stuff out beyond basic case classes to include those kinds of cases, but not much further. So ADTs, as far as shapeless is concerned, are things of this form, sealed traits extended by case classes, or things which are sufficiently close to that. And by and large, as a general rule, it just means things with just drop the case and add sprinkle lazy amongst the members, and you will again have something which is lazy val rather amongst the members, and you'll have something which corresponds to an ADT in Scala. So let's have a quick example of that, of one of these ADTs. Okay, I think there's enough pictures of cats on the internet. That's just one of those two will do. Okay, so that's ADTs. Type classes. Type classes in Scala. I guess everybody, I hope, is pretty much familiar with type classes, so I'm going to whistle through this really, really quickly. A type class in Scala is represented by a trait, which is indexed, which has a parameter, an indexing type parameter, which is going to be the type for which our type class is going to be instantiated. So it's going to be a trait, it's going to provide an operation, and given some data type, and we're primarily going to be interested in data types which correspond to ADTs, algebraic data types. So at the moment we're looking at the abstract animal trait corresponding to the root of the hierarchy we were looking at before. So we have a data type, and we will be providing an instance for that data type, and the instance is going to be an implicit definition of the trait instantiated at the type. Given that, then we can use implicitly to magically summon our instance for the given type from our implicit scope. That's a little bit inconvenient. We don't typically want to do that. Normally, we're going to be using this in the context of passing values of these types to polymorphic functions in the process of type inference and implicit resolution. An appropriate type class instance will be selected. Instead of having a manual implicitly, we would have an implicit argument list which pulls in the instance. Given the instance, we can then apply the corresponding operations to the values that we've been provided as arguments. This is still somewhat inconvenient, and it's become idiomatic to supplement type class definitions of this form with what's known in amongst the sort of the type level family of libraries as a syntax trait of some sort or another, and that's just basically going to be some form of I don't know, implicit class or implicit conversion to something. We're providing an enriched set of methods on our method that will take the type class instance as an implicit argument, which means it's available in the definition of the method we're defining, and that means that ultimately we can summon and use our type class instance in a relatively concise kind of way. We can make use of a context bound on the type parameter rather than the implicitly parameter block, and we can directly use the triple equals syntax in the body of the method, because the instance for EQ of t is going to be available in the implicit scope of the body of the method. So hopefully that's all pretty familiar for everybody, I guess. Is there anybody who's... Yeah? Okay, good, excellent. That's an interesting topic, but not one for now. So let's talk about it some other time. Okay, so let's have a quick look at an example. If anybody wants to grab, there's a code sample for this talk at that location. If you just head for my GitHub, it should probably be the most recently touched repository, because I only pushed to it this morning, so get it while it's fresh. That will contain all the code I'm about to show you. So let's have a look. What have we got? That needs to be a bit bigger, I think. Is that big enough at the back? How are we doing now? Better, but not good. Okay. Right. So, what we're going to do now is I'm just going to quickly walk you through with what you have to do. Just going back to that last slide. So the one thing I didn't show you here was what's with the ... on that implicit def. So to actually provide the implementation of the EQ instance for animal, what do we have to do? We have to write a whole bunch of code by hand normally. So let's have a look at what that looks like in this case. So here we go. We have our type class trait, EQ. We have an object, which is the companion object of EQ, which is where we're going to stash. This is fairly sort of idiomatic pattern for this kind of stuff. We've got a bunch of, if you like, default atomic instances. These are sort of the basic atoms that we're going to be working with. So we're going to provide a bunch of instances for integers and strings. The definitions hopefully are completely blindingly obvious what they're doing. They're just giving us an equivalence relation on our integers and strings. Okay. So we have the syntax type that we showed before. Here is our ADT, and here is how we provide the instance for our animal. Okay. Well, actually, before we do that, let's have a look at so we've got three types involved in this process here. We've got the animal trait at the if you like, the root of the ADT, and we've got a pair of case classes. Each of those things can have this equivalence relation defined on it. And I guess what we're going to do is we're going to see about, if you like, building up the overall EQ instance for animal from the EQ instances for a cat and a dog. Again, hopefully it's very, very easy to see what's going on in the case for the instances for the two case classes. We will just instantiate the type class at that type. We'll get a pair of arguments. We'll be able to use so we're actually defining the equivalence relation in terms of the equivalence relation for the integer and string types that are the members of the case class. So we're using the triple equals here, and everything works out really, really smoothly because everything's in the right implicit scope. We'll have the triple equals available for string and for integer in the bodies of the two methods for the equivalence definition for each of cat and dog. That's all really, really straightforward, nothing very exciting going on there. We just go case by case by case for each of the elements of the case class, just applying the corresponding operator to each of the elements until we get the final result. And okay, so that leaves the animal, the abstract, the root of the trait. Well, we get handed a pair of animals. We only have definitions for equivalence for corresponding types. So the typical thing that we want to do is do a pattern match. If we get a pair of cats, then we can we'll have a type which is refined to cat, and we can recursively invoke the equivalence relation specifically for cats. And we do the same thing for dogs. And if we compare a cat and a dog, then bad things happen. Okay, so that is so far so good, I guess. Is it? There's an awful lot of code there. An awful lot of code, and it's kind of fairly tedious, repetitive stuff. I mean, you can kind of see what you have to do for every single. I mean, we've got the boilerplate corresponding to the actual definition of sort of the instantiation of the equivalence class. We've got the boilerplate of the methods. So in the case of the case classes, we go. It's the conjunction of all the equivalence relations applied to each of the members of the case classes, and for the root of the data type, well, we've got this sort of splitting apart of the abstract type into its concrete cases, and then the application of the corresponding equivalence relation for each of those cases. So it's kind of, you can kind of see the sort of the conjunctions going off to the right, and we can see the kind of the disjunctions going from top to bottom. And it's very repetitive, and you could see if we added another animal, it's obvious what to do. But why do we have to do it? And I guess probably inevitably, if you end up doing this often enough, you'll end up looking at these kinds of things and wondering, wouldn't it be nice if the compiler could help me do that somehow? So this is what we're going to be talking about. And kind of the name for that kind of compiler helping me in this case is typically known as TypeClass derivation, as it comes from the Haskell world. Okay, so let's have a look. What's the history of doing this kind of stuff? So the first, probably not the first examples of this, but it's as far as back as I had time to look for today's talk. Sort of the Haskell specification, Haskell 98, defines, because obviously Haskell is, if you like, the locus classicus for the use of type classes as a general programming structuring model. So you'd expect to find people to have run into this issue in that context the earliest. In Haskell 98 specifies that built-in, hardwired into the compiler, there is the ability to basically go through that the mechanical motions of constructing the instances for ADTs for this half a dozen specially blessed type classes. So the EQ type class that I showed you, ORD is an ordering type class. Enum, oh god, I forget what that is. Read and show, sort of to string, and so a parse and an unparse. So these are hardwired into the compiler. They will give you instances for absolutely any ADT that you care to throw at them, but there's no extensibility there. You can't add your own type class to that list and have the compiler, the GHC, as of that era. Haskell compilers of that era, or at least conforming to that subset of the Haskell language to do for you. So a little bit later, and this is the sort of the development in the Haskell world that's most closely related to the work that I've done, is this really nice paper on basically extending that derivation model to basically well, not arbitrary type classes, but at least providing a mechanism that makes it possible to extend the set of type classes for which derivations can be done. So this is a really, really good paper, which I highly recommend. So that was published in that was presented at the Haskell Symposium in 2010, and it arrived in GHC in 2011. So the next step in this little bit of history is that Lars Hupel, previously of the Scala Z project and the co-founder of Type Level, he did some fantastic work on producing the first iteration of type class derivation for shapeless. He wrote a paper on that, which was presented in the Scala workshop in 2013, and he also provided the first implementation, which arrived in shapeless 2, which was around the same time. I can't remember exactly when. So what I'm going to describe today is the result of basically spending some time working with that and running up against some of its limitations. It's really great stuff. But it turns out that there's actually a much simpler set of abstractions which provide the same functionality and are much more general and much more flexible. And in fact, the type class stuff is able to be re-implemented in terms of it. So I did a whole bunch of work on that in Shapeless 2.1, which is relatively recently released. And I've just done a little bit more work in the last sort of month or so on sort of generalizing this even further to a whole bunch of really exciting new type classes, and that's actually something which is going to be very important, I think. I hope at any rate to the CATS library, because we'll be able to help ourselves to mechanisms for automatically deriving type class instances for most, if not all, of the CATS type classes. That's the history. Okay, so back to the ADTs again. Here's another example of the simple ADTs. We've got our sealed trait. This is one with a type argument in it, and a pair of case class case class instances of elements of that algebra. The way that we tend to talk about these things, at least when we're thinking in terms of generic programming, is to think in terms of sums of products. So because the root trait is sealed, there is a fixed set of types which it can be extended by, and we can view those as a kind of disjunction. Anything which is a tree is going to be either a leaf or a node. So it's this or that, and we can imagine extending that list of possibilities more or less indefinitely. When we look at the different branches of the ADT, the case classes, again we can see that there is a corresponding kind of sequence, a sort of list-like thing, corresponding to each of the elements, and these we describe as product types. I think it's reasonably helpful to think of this in terms of some kind of a branching structure. We can put a root of a data type which branches to give us which is a sum or a coproduct, and the leaves of the ADT which are product types. In terms of the actual concrete types that are used to represent these things, people who have spent any time at all with Shapeless will know that Shapeless has for a very long time had things called H-lists. I now kind of wish I called them something different, but it doesn't really matter. H-lists are, if you like, the things which represent the double colons, the sort of the collection of elements of a case class. Slightly more recent arrival, they arrived in Shapeless 2, the colon plus colon thing, the coproduct types, which represents basically, if you think of H-lists as being roughly speaking nested pairs, you can think of coproducts as being roughly speaking nested ithers. So there will always only ever be one inhabitant of the coproduct type at the top. It'll either be a leaf or a tree. and each of those things will have some number of elements represented. Okay, so that's the background. So what I want to show you now is I'm going to take you first back to that EQ example, and I'm going to demonstrate how, as of shapeless 2.1 or 2.2 release candidate 1, we can completely automate the process of providing instances of that case class for arbitrary algebraic data types. So not restricted to some specific set, but for all of them. So you have to write it only once and never again. So let's have a look at some code. Right, so we remember the example we gave. So this is the code that we wrote by hand. So what we're going to want to do is come up with some mechanism which allows us to essentially delete all of that stuff. So let's have a look. What have we got? Right. So we have the same trait. We have the same two manually provided instances for the non-ADT things that we're going to be working with here. So we got instances provided for integers and strings. They're exactly the same as the ones we had in the fully manual version that we had before. So the exciting stuff comes next, and this is an instance for any type which has a generic representation. Okay, so this is going to give us an instance of EQ of t. That's the one that we're materializing at this point. And we are doing that via an instance of this generic type class. And what the generic type class is going to do is it's going to map our ADT element of type T onto some type R, a representation type. Then it's going to define the EQ type class for the original type T in terms of EQ defined on the representation type. So we're going to take something which is concrete and specific, which is written by hand, like one of those ADTs family, a sealed family of case classes. It's going to map it into a completely general and generic representation, which preserves all the appropriate, all the relevant type information about the original type. It's going to perform the equivalence check relative to the representation type, and then it's just going to give us back the result corresponding. Well, I mean, in this case, because the result is just a Boolean, there's no mapping back to be done. We are done via the equivalence over the representation type. So hopefully it's kind of reasonably clear what's going on. For the moment, don't worry about this lazy thing. I will hopefully touch on it a little bit later on, but just forget that it's there, and also forget that the dot value that will appear is there as well. So what's happening is that the generic instance has two methods to find out. It has a method to and a method from. The method to will take a value of the case class type, the value of the ADT element type onto the generic representation. So we're mapping both x and y into the representation type. We're using the equivalence for the representation type to compute the Boolean value, and then we're done. That's it. That's all we have to do at this point. Okay. So how do we compute, in general, this type class instances for these representation types? Well, if you remember what we had over here, we had essentially two cases. We have sums, which are things like either a leaf or a node, either a cat or a dog, and we have a case for the products, which are going to be, in the case of our animals, a name and some amount of food. So in other words, a product which is going to be effectively a collection of the elements of which form the content of the case classes. Okay, so what does that map into? Well, we have two cases represented here. We have essentially an inductive step over the product. So our representation is going to be an H-list which consists of a sequence of the elements of our product types terminated with a sort of a terminating nil element. And we're working through this inductively, so we will have a base case for, well, how do you compare empty representations for products? And the answer is, well, you've got two empties, they're obviously the same. How do you compare? So that's our base case for induction. This is our induction step for the product, and this is sort of given a head and a tail. How do we do the comparison? Well, we do the comparison for the head, and we do that in terms of an instance of the type class for EQ for the type at the head, and that will be potentially that will correspond to either, say, the int or the string instance that we've defined earlier, but in this specific case. So we can do a comparison for the head, we can do a comparison for the tail, using the corresponding equivalences here. And hopefully it should be reasonably clear that this corresponds pretty directly to the manually written definitions that we had in the earlier case. The difference being that rather than it being, if you like, hardwired into the definition, we've got something which has a sort of a recursive list-like structure which we can effectively fold over. Okay, so that was the case for products. And then we have the corresponding case for co-products. So this is for the cat or dog case. And again, we're going to be basically inductively walking down this if you like, set of nested eithers until we reach the end of the nested eithers. That's going to be our senior case here. So that's corresponding to the end of a sequence end of a sequence of choices. And again, if we kind of get down to the bottom, I mean, this is a slightly kind of absurd case because you would never get to C-nil, but in any case, we're going to treat that as being analogous to the H-nil case and define that as true. And as far as the body is concerned, well, we're doing something which is again somewhat similar to what we were doing with the in the manual case, where we're looking at we're doing a pattern match, this time not on the specific type constructors of the case classes, but on the constructors of the coproduct type, which is, again, this is our effectively nested eithers. So this, you could, if you wanted to map this back into the standard Scala either type, we could be looking at sort of two things on the left. So that could be two cats, or two things on the right, which would be two dogs. In which case, we can use the corresponding equivalences for having refined the types to something for which we have an available product instance. We can compute the right result, and if we have a mixture of cats and dogs, then again we produce false as the result. Okay, so that's the mechanics. And basically that's the core of what I'm going to show you today. I'm going to show you a whole bunch of other examples of doing the same thing, but essentially that is the mechanism that's involved. We have ADTs, which are sums of products, and to define an automatic derivation for a type class for arbitrary sums of products, arbitrary ADTs, what you have to do is provide these two inductions, one over products, one over sums. And having done that, there is no more to do. That is the end of the story. So here again are our two, here's our ADT, and we can just do a quick demo of this, I think. So, oops. Yes. Big enough? Where am I? What was it? What did I call that object? Oh, did I not do that? That would help. Thank you. Sorry, getting there. Okay, so we've got two values of our type, and we can compare those using our That's not, no. Okay, so a quick explanation of why that was not execution cost. That was compile time cost. So remember that every time you hit return on the REPL, it will be compiling the line of code that you've entered. And what has happened at each time I hit return is because we've not created a, sort of, if you like, a cached pre-computed instance of the type class we've just derived. So we just derived equals for animal. We're doing that every time. In practice, what you would do is you would do it once. You'd cache an instance, probably in a companion object of the type that you were defining it for. So there would be a once-off payment of compile time for that. As far as runtime is concerned, basically the runtime is. There is a small overhead because we're working with a generic representation, so we're mapping the case classes into the generic representation and back. But it's not, you know, the representation in terms of H-lists or co-products is roughly speaking the same as the representation in terms of either or lists. So it's, you know, there is a penalty to be paid, but it's not enormous. Okay, so. Can everybody see what's happened here? So shall I? I'll take some questions now. Actually, any? Yes.
Yeah, you mentioned that you want to cache the results of the derivation, which ties into a question I was going to ask about how to scope down the derivation. Like, I would not want just any ADT necessarily to be beyond what it being derived into an equivalent type class or anything of the sort. So is there a sensible way to kind of scope down the derivations and just expose the results of the derivation to the end user code?
Yes, I mean, all of the techniques that you've used for controlling the visibility of implicits apply here. I mean, there's nothing special, there's no magic. Everything is just standard implicit resolution. So the same techniques apply that you would use to control visibility anywhere. If you want, if you make the generic deriving infrastructure part of the companion object of your type class itself, then it will automatically be available to all ADTs without exception. But there's no particular reason why you have to, you're not obliged to provide the generic deriving infrastructure on the companion of your type class. You could provide it somewhere else, and then you could restrict control of derivation based on where the visibility of those things were. I actually think that if you've gone to the effort of writing a deriving, bearing in mind we're talking about ADTs here, so we're talking about a restricted set of Scala types. If you've gone to the effort of writing the deriving infrastructure, why would you not want to have things derived? What possible objection do you have for it? I mean, if you don't need these things, you'll never touch them, you'll never use them. There'll be no either compile time or runtime penalty for their presence. There was, in an earlier iteration of the type class derivation mechanism, there was like a gating import that was required to enable it. In practice, it was just noise, and there really didn't seem to be any benefit from having it beyond what you might just want to do in general in terms of managing implicit visibility. Any other questions? Is it? How about? Yes.
How did it get from the Scala seal traded into your like H-list format?
Right. Okay. So that was the responsibility of the generic instance that I showed you at the top. Let me go back to that. So this is something that has existed in shapeless from where I missed it. Where did I leave it? Where did I leave it? Here we go. Right. So we have this generic type here, and so if we ask for the generic for animal, and then to apply that to an animal, what that's doing is, well, okay, it's not completely obvious what that is, but that is what is that? That's probably I think it's probably that. Oops, in R. So the generic will map sealed traits at the root of an ADT into a coproduct type, which is what's happened here. So we've had our Tigger here is typed as an animal, and so it gets mapped. So when we run that through the generic, we get mapped to effectively a nested either of cats and dogs. Hence the wrapping of the value in the right, effectively. If, on the other hand, we were to apply that to, if we were to to a product type, so one of the case classes directly typed as the case class. So we're using a different. This is a different generic. This is going to map us onto an H list of the elements of the type. So so the generic itself is the mechanism that takes us from ADTs to the generic representation, and the rest of the infrastructure is just a pair of recursions over the generic representation. One for the coproduct part of the process, and one for the product part of the process. How much time do I have?
You've got about 7 minutes.
7 minutes left. Okay. Damn. Okay. I will probably show you fewer examples than I was intending to in that case. So I'm going to come back to. Let's have a look. Okay. Well, we can repeat this process sort of more or less ad nauseam. Actually, before I continue, does everybody believe that I've actually done that one? That's enough for EQ defined for all ADTs. Does everybody actually believe that? So you never have to write that manual code for another ADT again. So I mean, we could just have some other completely different ADT. So this is completely separate from anything I've done. There is nothing prepared previously for this, but I can happily reuse the same deriving infrastructure, and that will again just work. So there's no. This is completely generic. Any single ADT. So that was for a case class. If I define another sealed trait, exactly the same thing would apply. All of the same mechanics. It's there for everything. You never have to write this again. Okay. So having done that, then obviously the answer, the next question is, well, how many different kinds of case class, different kinds of type class is this available for? And the answer is an awful lot of very useful things. So we can do orderings. So this is a standard kind of ordering type type class. This is derived in almost exactly the same way, exactly the same pair of inductions over products and coproducts. We can define monoids, so this is a sort of a natural product-only monoid. We can define, well, there's a whole family of things which relate to serialization and deserialization type things. So we have a show type class here. Just zipping, so this will provide an automatic derivation of show. Show itself isn't very exciting because obviously everything in Scala has a two-string. For better or for worse, but we can apply the same kind of general principles. A pair of recursions, one over co-products, one over products. That's lent on heavily in Scodec, which is a fantastic piece of software. That's from Michael Pilquist. Alex Archambault has put together a very, very nice and very, very simple. It's actually an adapter layer for Argonaut, the JSON codec, making use of shapeless. And I just want to very, very quickly show you something there because I think this is demonstrating that it's actually incredibly straightforward to add this to your own serialization. So this is half of the whole thing. So this is the side of Argonaut shapeless which does the encoding. So this will take take ADTs, not just case classes, ADTs onto JSON. There is another piece of code which is almost exactly the same length, going back in the opposite direction. That's it. That's everything. It's a tiny, tiny little library, just defined in terms of a pair of recursions, one over co-products, one over products. That's the only stuff you'll ever have to write. Another example is, so this has been also used by, it's being used in Enzyme, and Enzyme has a very, very fairly rich and complicated protocol, which is represented by case classes for communicating between Emacs and the Enzyme server. That's currently using shapeless, using this type-class derivation mechanism for serialization and deserialization. And there's a whole bunch of little examples in the shapeless repo. Okay. One more example, and then, because this is kind of exciting stuff, which is relatively recent, which I would quite like to show you. And that is, I mean, one of the things that sort of, I think a lot of people have thought about some of this generic stuff is that it's all about serialization and deserialization. That's really not the case. And one of the things that's recently arrived as of shapeless 2.2 is that we can now we've generalized, I have generalized generic to not just first order types, but also to higher kinded types. So we can now have generic representations of parameterized types, in particular, things like list or option or any kind of type that you might think of which have a hole for one type in. So here we have a very, very similar to the thing we showed before, derivation of a functor type class. So functor basically captures the notion of map that we're familiar from list and option, but in much greater generality. So we're going to be mapping over our sort of notional container of things, transforming content of type A to content of type B. So we can do this, we can define this in a completely generic way. And here we have an example of the way the derivation goes. So similarly to the way we have manually provided instances for int and string in the first order type cases, we have a manually provided case for the ID functor. But then we just have the same pair of recursions. In actual fact, because of some subtleties about how this had to be defined to work with higher kinded types, if anything, the definition is somewhat more compact. We just this hcons and ccons case, both of those two methods, each of them capture the entirety of, in the hcons case, the recursion over the product part, the higher kinded product, and in the ccons case, the higher kinded co-product case. And then it's just simply a matter of, given a generic for a generic one, so this is a generic for the thing with a hole in it, we can map a value of that type into a representation type, perform a generic map on it, and then map the result back across the generic in the opposite direction, back to the original type we had. So a quick example of that is, say, here. So here we have a tree ADT. So this is a tree of T. So this is new. This is not stuff that could very straightforwardly have been done in shapeless 2.1. So it's a tree of T. We have leaves of T, and we have nodes which have a parent. So it's a binary tree. There's a value of that type. So I'm going to very quickly. So here's our tree. And let's just map something over that. So what should we do? Let's map length. And I get a tree of integers. And I haven't written any manual code specific to that tree data structure. Everything has been derived automatically just in terms of the algebraic structure of the constructors of that the structure of that algebraic data type. Everything has been read off those 3 lines of code which specify the ADT. And for that we get a functor for free. I think I'm going to stop now because I'm pretty much out of time and I'll let you ask questions. But this generalizes. Very recently, in the last week, Kenji Yoshida contributed a definition of foldable, so we can have a generic as well as a generic map. We can have a generic fold. There is if you like, a small tower of type classes, interrelated type classes in the CATS library in Scala Z. These things can. I won't say that. In some cases, for some kinds of ADTs, they can all be derived. In other cases, parts of the picture can be derived and parts of the picture have to be provided manually. But using this kind of mechanism, we can take those very, very general abstractions and we can help ourselves to implementations of them for a very wide range of data types completely for free without having to write any code at all. I think that's kind of cool. Okay, I'm done. Questions? Yeah, that was you, sorry.
Okay, exactly in this tree example, how much adaptation would it take if you say that a node would be able to take an arbitrary, arbitrary is a dynamic amount of subnodes. So when you say a node is actually not an element, arbit is a list of trees of T.
Well, that's free because list is an ADT. The standard vanilla Scala list is an ADT. I haven't actually shown you here. List is a bit weird, but it is actually sufficiently like the canonical example of an ADT that it does just work with this infrastructure. So I can derive these instances for the standard Scala list, standard Scala option, any case class with a type variable in it if you wanted to, or pairs, all of these things, absolutely everything. Anything which conforms to a sum of products that you care to represent can be treated in this way. Absolutely everything. So if you were to replace the pair of the left and right with a list of node, that would just work. Do I have time to just demo that if you don't believe me? I mean, I'll show you later if you want to see that. Yes, Daniel.
Can you derive something more complicated like that?
I'm getting there. Yes is the answer. In principle, yes. Basically, if you look at the stack of type classes, there are various different pieces that you need, relative to a given data type, some of these things will just be possible to read off the constructors, and in some cases you'll have to provide something specific. So, for example, for list, you can read, say, pointed off the constructors. So in other words, a way of going from a value of type A to list of A, you can just read it off its constructors because we have a cons node which takes an empty thing. So you can work out that there is only one way of constructing a one element list. That can be done. In fact, Pascal Voitot, aka Mandubian on Twitter, just did that the other day, yesterday. So that's absolutely possible to do. You can derive functor for list. You can derive foldable for list. We've got pointed. The one thing you can't define, because it doesn't have a natural thing that you can read off constructors, is if you like, monoidal append. But if you provide that explicitly, then I think we're there. Actually, I think that's all that you need, and that can give you the full applicative stack up to monad. If it doesn't get you all the way there, we're very close. And there's going to be basically one or maybe one more small piece that you actually have to provide explicitly. But basically everything else comes for free. So part of what I think is exciting about this structure is that you get a kind of a lot of these type classes, they come in, if you like, little clusters of interrelated concepts. And there are relations between them, and in some cases, given one or two, you can get all the rest. It's not necessarily the same one or two in each time, in each case for a given data type. But in most cases, there will be at least some work that you don't have to do because if you can help yourself to this kind of infrastructure. Anyone else? Is the guy with the hook coming to take me off the stage? Any more questions? One more? Yes, go ahead.
Yes, practically, have you used this library for tensor product?
Oh, yes. Okay, so there's a whole bunch of stuff coming in shapeless 3, which is basically I realized sort of middle of last year that there is a fantastic unifying generalization of products and co-products via sort of fantastic concept known as a symmetric monoidal category, which basically mashes all of these things together. So instead of actually needing those two separate recursions, one for products, one for co-products, basically it's the same recursion. And the same thing, these are products, co-products are these beasties. Tensor products are also another example of the same thing. So yes, absolutely. And there's a whole bunch of really, really exciting stuff there, which incidentally is related, the underlying mathematics is actually quite closely related to the mathematics of Aikmet's lens library. It's very, very closely related to that stuff. Any more? Yes?
How does generic work internally? To rephrase, how are you internally getting that instance of generic that allows you to map ADT to?
Yes, generic and generic 1 and what will probably be the family of generic n that follow on from it. They're implemented as implicit macros. There is no way of well, there is a way of implementing generic for product types only. So it's something that was called ISO in shapeless prior to shapeless 2, and that can sort of piggyback on case class apply and unapply to kind of extract out, if you like, the content in a generic way from case classes. But it was never possible. It was never going to be possible to extend that to co-products to the sealed families of types. So generic. As far as the stuff I showed you there, everything was completely vanilla, implicit, and type inference driven Scala code, with the exception of essentially two macro primitives. One of them is generic, which does this mapping between ADTs in Scala and a generic representation, which has to be a macro. The other is the lazy thing, which I kind of brushed under the carpet a little bit. Lazy, so a lot of these structures that you're seeing are sort of recursive, and we're stitching together interesting recursive operations over recursive data types. And under normal circumstances, if you wrote code like that without lazy, you would immediately have run into problems with implicit divergence. So what the lazy type constructor does in the context of this stuff is basically give you a mechanism for controlling divergence and effectively tying implicit recursive knots. So it builds a little dictionary of type class instances and allows you to stitch those things together in a manageable kind of way. And that's crucial for getting the recursive data types working correctly. Anyone else? Yes?
So if we're going to install this in a medium or larger code base, are we going to pay a penalty?
It depends. Well, it depends. I mean, no, this should play nicely with incremental compilation. I mean, if you don't, so the only time that one of these derivations would need to be recompiled is if you modified the ADT that it was that it was being an instance was being derived for. The cost of the derivation of that instance. I mean, you saw there was a definite noticeable pause when I was hitting return. This is a kind of a one-off cost mostly that you pay. And it's very much related to, if you like, the size and complexity of the data type. If you throw an ADT with 20 branches, each of which contains 20 members, then you'll have time to make a cup of coffee while you're compiling it. And there is some stuff that I'm hoping to do for Shapeless 3 which may address that. I don't really know. And I think I've made a fairly deliberate choice as far as Shapeless is concerned. Is whenever I have had to choose between performance, be it compile time or runtime, and expressive power, I've picked expressive power every time. And so those are the breaks. I mean, you kind of either use it and it works for you or not. I think there is a definite place for this kind of stuff. Okay, I think that's probably time. Thank you.